Good day, my name is Podgrudkov Dmitry. I am an assistant professor at the Moscow State University, and I'll talk about extensive air showers. Extensive air showers are the cascades of elementary particles initiated in the Earth's atmosphere when a primary cosmic ray particle enters it. Primary cosmic rays are the flux of the high-energy nuclei coming to the Earth's atmosphere, flux of the primary cosmic ray radiations, the flux of all particles stable, or even not yet discovered dark matter particles coming to the Earth. Low-energy cosmic rays are detected at the Earth orbit by the spacecraft, but the Earth's atmosphere isn't that thin. The particles of the high energy, even the highest energy, cannot get to the bottom of it. The equivalent of Earth's atmosphere is around 10 meters or 90 centimeters of lead. Even the strongest particles will interact long before they reach the Earth. The composition of the particles above the atmosphere is mostly protons, but when they do interact below the atmosphere, we get different composition, mostly gamma quanta, muons, electrons. The Earth's atmosphere is quite thick. It's equivalent of 10 meters of water or 90 centimeters of lead. Particles, charged particles, even with the highest energies, cannot reach the bottom of it. They will interact way earlier, producing in nuclear reactions the secondary cosmic rays. Composition of the secondary cosmic rays are way different from the primary cosmic rays above the Earth's atmosphere. If above we had mostly protons, below atmosphere we have mostly electrons, muons, gamma quanta. Nuclear reactions at high energy have peculiar properties. The number of secondary particles, so-called multiplicity, is actually random in each event, but the average number changes weekly with the energy, like its logarithm. This means that high-energy particles produce secondary particles and transfer them energy. The higher the energy of the primary particle, the higher the energy of the secondary particles will be. Their numbers didn't change with energy. So, the secondary particles might be the high-energy particles themselves and do initiate nuclear reactions that will produce tertiary particles that will also have high energies, and so on. In 1938, Piaget, a French scientist, discovered that secondary particles of the cosmic rays come at Earth level in tight groups. He proved that they are connected and should have been created within some single event. He discovered extensive cosmic ray showers. How exactly this happens? These showers. When the primary particle reaches the upper layers of the atmosphere, let's take it about 100 kilometers above Earth, it first travels some distance before it interacts. It will interact somewhere about 20 or 30 kilometers above ground, depending on whether that was a proton or an iron nuclei, and produce some secondary particles, mostly pions charged neutral, lightweight, short-lived particles. Then it will transfer half of its energy to those particles, and leaving much more of its own energy will follow down the atmosphere, producing secondary interactions, giving subcascades below. This is called as a leading particle. The line along which it travels is called the axis of the shower. But back to the particles that were born in the first interaction. Neutral pions are very short-lived. They live something like a tenth of a femtosecond and decay almost at the pace they were, not even a millimeter of travel. And they decay into most probably 2 gamma quanta, rarely 3 gamma quanta of the high energy themselves. Those gamma quanta travel in the atmosphere and in some random nuclei produce electron-positron pair each. Those electron and positron pairs are of the high energy themselves and can, in what the process called Bremsstrahlung, the radiation associated with the quick deceleration of elementary particle, charged elementary particle, produce gamma quanta of the high energy again. Those gamma quanta will produce more electron-positron pairs, they will produce gamma quanta, and so on. In short, the gamma quanta produce electrons and positrons, positrons and electrons produce gamma quanta all along until the energy is depleted. Energy conservation law actually means that the energy of the primary pion is redistributed between secondary particles. At some moment, the number of particles grows so large they have each individually a small energy. Not enough for a gamma quanta to produce a pair those gamma quanta will scatter off electrons and nuclei and get absorbed by the atmosphere, and the electrons will quickly lose the energy on atmospheric ionization. It takes some energy to ionize an atom, and that means they will lose energy quickly and, well, stop and get absorbed. This is all together called electromagnetic or electron-photon cascade. It is not a long process, it happens relatively quickly. It doesn't take the whole atmosphere to stop any number of gamma quantas at high energy. They will disappear. But let's return back to the original pions. Charged pions travel further a bit than their neutral counterparts, since they live longer, 10 nanoseconds, or something like that. And they do have chances to interact with the nuclei of the atoms. Those interactions are alike to the primary one and do produce secondary pions, or some other short-lived particles that do interact with atomic nuclei, producing more pions, and so on. What we see is the same idea of a cascade, but now it is called hadronic cascade. The hadronic cascade in the atmosphere travels along its path, and it transfers some of its energy to the electromagnetic cascade, since in the interactions of the pions, more pions are born, and some of them are neutral that will decay naturally. This process and hadronic shower will naturally go until the energy of the pions is depleted. Again, it's redistributed between different particles that have the same initial energy. When the energy of a single pion drops below what is called critical energy, it has more chances to decay than to interact. The interaction starts another cascade, but the decay, it's the end of the hadronic cascade. Decaying pions decay into muons and neutrinos. While the neutrinos are, well, part of the hadronic cascade, they're so weakly interacting with matter, then they are no longer considered the part of the shower. They are a different story in the cosmic ray studies. The altogether number of particles in the cascade changes as the cascade develops. The number of particles at a given height or depth in the atmosphere is called the cascade curve. You can see it on the image. An extensive air shower is in short a cycle of particles being born. The particles travel to the Earth and form some volume. Piaget in his studies found out that these cascades span few meters wide. This is caused by the fact that when the particles interacting, the secondary particles that were born travel at some, might be small but not zero, angle regarding to the direction of the initial particle. This means that the particle of the next cycle, and the more cycles it happen, the more particles get spread further and further in angular terms, and since they do travel, it means they spread wide. Despite the fact that most of the particles will be within something like 70 meters around the shower axis, the outliers will fly far, few kilometers from the shower axis at the most of the highest energies. However, in the thickness terms, the shower is small, surprisingly. Only a meter or so in the middle, and while something like 100 or 300 meters at the edges at the most highest energies. On the animation, we can see the live data recorded in the Sphere 2 experiment in 2012. These are the particles that hit the ground at certain moments in time. The field of view is around 200 meters, the time is nanoseconds. The speed at which this stripe moves indicates the angle at which the initial particle of the cascade hit the atmosphere. If all the particles to be combined on the observation plane, e.g., where they all hit the ground, the distances to the shower core form what is known a lateral distribution function, the density of particles at different distances from the shower axis. The shower is axisymmetrical at most of the times. These curves, along with cascade curves, are crucial to understanding what the initial particle was. These are recorded in each and every experiment and are studied. But how do we study them? To study extensive air showers, we need to begin with the registration of the uncharged particles that form that cascades, that form that showers. Many different types of the detectors do exist, but only a few are used in the cosmic ray physics. When a charged particle enters the volume of the detector that is filled with noble gas and a strong electric field, it starts to ionise the gas. The resultant electron-ion pairs in the strong field becomes separated. The ions begin to drift towards the cathode, electrons to the anode. In the strong field means that after a certain travel distance, small one, ions and electrons will gain enough energy to ionize gas themselves, producing more electron-ion pairs, producing more ionization. This results in a strong electric current pulse in the counter. In some sense, electric-wise, this is equivalent to a charge capacitor being short-circuited by an elementary particle. Right now, as of today, Geiger counters are left only in some historical devices and installations, are not longer used, but they were used in the past. Piaget used these counters to discover the extensive air showers. The first installment of the Moscow State University air shower array was built around them. Later, they were changed by these scintillation detectors. The scintillation detectors are a type of a detector that actually emits light when a charged particle enters it. What happens is that when a charged particle travels through the media, it ionizes and excites molecules of that medium. The excitation process and recombination results sometimes in a light being emitted. In general, materials are opaque to this emission and they do absorb those photons. But in some cases, in some materials, those photons, that light is not absorbed, can exit the material and be registered. These materials are called scintillators. Scintillator detectors consist of this kind of material, a plastic or inorganic crystal, and a usable photodetector. These are, as of now, the scintillation detectors are a staple of the cosmic ray detection. They are used both in orbit and in the ground arrays for the extensive air shower registration. Another type of detector is a Cherenkov one. If a particle is traveling through the media at the speed that exceeds phase speed of light in that medium, and that happens, the light travels in the medium at the speed lower than it does in the vacuum, so the charged particle can outrun it. And when it does, the medium in response produces a Vavilov-Cherenkov radiation, blue light, associated with the charged particles. The atmosphere itself is a medium. Charged particles within the atmosphere do produce Cherenkov light, a small number of photons, but they envelop the cascade that develops in the atmosphere and come to the ground. Since the photons of Cherenkov light are not absorbed by the atmosphere much, they reach it, forming what is known as Cherenkov flash. These Cherenkov flashes are detected by various number of present-day detectors, most prominently in the gamma ray astronomy for the ground-based experiments at least. Another type of the detector is a Cherenkov detector. If a charged particle enters a clear medium, it does produce Cherenkov light. These type of the Cherenkov detectors are filled with water. They register Cherenkov radiation produced by charged particles enter their volume, simple as that. The practical and the best thing about Cherenkov detectors are that they can be built to any configuration and they can be made really large. On the screen you can see a water tank from the Piaget Observatory. It is something like 3 meters in diameter, while the usual scintillation detectors used previously cover about 1 meter or 2 square at most. Another effect we should mention is the fluorescent light. The fluorescence is a non-thermal emission of a material when it absorbs some energy. The charged particle traveling through the medium, the air in our case, does leave some energy to the material in form of ionization. Roughly speaking, the charged particle traveling through the air ionizes it, and in doing so it ionizes nitrogen molecules and excites them. Some of them, due to the special properties of the nitrogen molecules, do emit fluorescent light that is not easily absorbed by the atmosphere. This means that each charged particle in the air produces about 5 fluorescent ultraviolet photons per meter of its track. This results in the shower being enveloped in an ultraviolet glow. The more particles there are, the more fluorescent photons are being born. So this means we can see the shower cascade as is from a distance. So how the detector should be arranged to measure extensive air showers? Well, at the lowest energies, when almost all the charged particles get absorbed by the atmosphere, only the Cherenkov photons reach the ground and can be detected. For the lowest energies, the Cherenkov telescopes are used. Small like this in the picture from the Tunka Valley, only 6 meters in diameter, or large as this one in Namibia, spanning 28 meters in diameter. They register Cherenkov light, its angular properties, and the number of photons. The image, light spot properties, its size, orientation, are the data for the reconstruction of the primary particle type and energy. Another option for the low-energy showers, but with some particles still already reaching the ground, are the tight arrays. Detectors are packed close together, as in the picture of the Hawk array. You can see water tanks there, and those are filled with water, each about 200 tons. They register charged particles via Cherenkov light in water. Each detector is overviewed by 4 photomultipliers, photosensors, that measure the brightness of the flash, e.g. the number of particles, and the exact time they arrived, sending all that data to the central facility, where from the number of particles and the arrival time, the arrival direction of the primary particle is deduced, its energy and its type. Another example, classical example of the tight arrays is the cascade experiment. You can see in the photo the houses, the house, shielded from the weather, scintillation detectors, 1 or 2 square meters each. After some upgrade, it was the cascading Grande array. You can see the location of the initial array on the right side. It was updated with underground muonic detectors. The muonic component is crucial to understand whether it was protein or iron at the beginning of the shower cascade, but the muonic detectors are hard to construct. They require shielding from electrons, and that takes some work to be done. Usual way is to bury those detectors underneath the soil. Few meters of soil, no electrons can pass, but muons do. Another approach to tight array is to observe a shower from above. You can see Sphere 3 on the picture, the LSO, the data from its predecessor, Sphere 2. This is a new experiment. It observes the snow-covered surface, and when a shower, specifically Cherenkov light of that shower, hits the observation plane, you can see how this spot will look like from the something like 500 or 1,000 meters from above. It will record short video that will be analyzed later. However, these are the results for the arrangements for the low energy or middle energy particles. The high energy showers may be registered differently. Since particles of the cascade actually spread far, you can space wider the detectors. Each will register particles from different cascades falling all around it in some radius. Well, the data from one detector isn't enough to understand anything, but if we have an array of detectors, we have enough data. On the picture you can see a Tianshan high-altitude astrophysical station. Yellow lights indicate the directions to the individual detectors. Some, the first one, was spaced by 2-kilometer distance. The Tianshan is constructed primarily of scintillation detectors, and still the stations are connected to the central facility via the cable. In Tunka Valley, we saw a telescope from there, but they do have what is known in Cherenkov array, the array of detectors of Cherenkov light. These are photodetectors, photomultipliers of the previous installment Tunka 25. The present-day Tunka 133 houses newer detectors, wider, but they do observe Cherenkov light from showers. This array has almost no capability of registering elementary particles themselves, only accompanying Cherenkov radiation, but it's enough to measure their energy and their type. Another way to do this thing is use scintillation detectors, as in Yakutsk array near Oktyabtsi, Sakha, Russia. That is an array of scintillation detectors. Some of them actually have Cherenkov stations in them, spaced around 3.5 kilometers. You can see the stations marked on the map here. They are still connected in the facility, but this is possible only for the rays like this, 7 or 10 kilometers of effective registration area. But the registration area for the highest energy may be way bigger, like 100 square kilometers, as was in a gas experiment near Kino in Japan, or reaching up to 3,000 square kilometers, as in the Piaget Observatory in Malargüe, Argentina. The setup for those spaced and very dispersed experiments are very different. You can see on the picture the detectors of the telescope array experiment before their deployment. They are autonomous. Each one registers particle individually, cannot guess, is it only a single particle coming at random, or is it a shower and there are different particles in different detectors. It just sends the data using its antenna to what is known as central node. A lot of them. That node decides whether there is enough particles to consider this as a cascade or not. Then it sends data to the data center. Complexity of this grid and planning, well, is obvious. It's not an easy task to do such an experiment. And to go bigger, the biggest to the date constructed air shower array installation. The largest constructed air shower array to date is the Piaget Observatory. It is aimed at registration of the most energetic particles that has a low flux, something like 1 particle per 1,000 square kilometers per year. It is constructed of 1,600 water tanks, overlooked by the 4 fluorescent telescopes. Fluorescent telescopes' construction resemble those of the Cherenkov telescopes and can be seen on the photo on the right. The fluorescent light itself is produced by charged particles traveling through the air when they do excite nitrogen molecules. Nitrogen molecules emit those photons in ultraviolet region that travel at random directions. This is a blessing and a curse. The photons disperse, which means only cascades with most particles in them can be registered. But all the directions that ultraviolet photons fly means they can be seen from any direction. The fluorescent light telescopes observe high distances reaching up to 30 kilometers in case of the Piaget Observatory ones, covering about 1,000 square kilometers in area each. The extensive air showers are a part of the cosmic rays study. The cosmic rays are a known phenomena for long but not yet fully understood. The new detectors are being constructed, the new ideas and theories emerge, but there are still things unknown and undiscovered.